I'd like to show you how to make a simple physical model of how some materials deform when they are stretched or shortened. I use stretchy cloth that is sold in fabric stores as swimsuit liner. The fabric is attached on one end to a ruler and on the other end to a flat wooden slat that is attached to a small sheet of melamine or masonite. Let me show you how it all goes together. First, we spread the stretchy fabric on a table so it is in its relaxed state. Taking a carpenter's square and a silver Sharpie, we draw a rectangle that is 8.5 inches wide and about 21 inches long. Using scissors or a craft knife, we cut the rectangle out. We wrap the fabric around the ruler several times in the same way we will wrap it when we do the final construction of the model. We use something circular as a template and draw a circle on the cloth. This circle will help us define the initial unstrained state of the cloth. We cut a piece of 1/8 or 3/16 inch melamine board to be 10 inches wide and 14 inches long. Melamine is a white finish they put on classroom whiteboards. We also need a ruler, a 10 by 1¼ inch piece of masonite, a strip of rubber padding used to line tool drawers, the rectangle of stretchy cloth, and some binder clips. Now it's time to put the model together. We wrap the fabric around the ruler on one end, then we wrap the other end around the masonite strip. We put the rubber padding under the masonite to keep the fabric from slipping. Then, we use the binder clips to attach the masonite to the melamine board and the fabric to the ruler. A couple of small clips are put near the end of the melamine board to act as stocks. When we stretch the fabric, the ends of the ruler are held by the wire handles on the two small binder clips. The simplest experiment is to stretch the fabric and see the initial circle stretch into an ellipse. Adding candy dots to the experiment helps us to visualize how a triangle of GPS sites would move if subjected to one-dimensional stretching. The real fun comes when we put dry powder on the fabric. Dry powder is a weak material that can fracture and fault. We use 1/4 inch square dowels to help us make a layer of powder that has a uniform thickness. Wallboard joint compound is used as a powder in this experiment, but dry flour will also do. A wallboard taping knife is used to spread the powder to a uniform thickness, dragging the knife along the top of the wooden dowels. Then we use a cardboard sample tray or an index card to smooth the powder. With the layer smoothed and ready, we stretch the layer by pulling on the cloth until the ends of the ruler can be slipped over the binder clips. Sets of mode 1 and mixed mode cracks cross the layer approximately perpendicular to the direction of stretching. Next, we make a slight circular imprint on the powder. We're using a petri dish to make the circle in this experiment. Don't make too deep of a mark in the powder or else it will affect the results. When we extend the layer, cracks develop and the circle evolves into an ellipse. The long axis of the ellipse coincides with the direction of stretching. While deformation in the layer is discontinuous, the initial circle still evolves into a reasonably clear ellipse. Next, we add 3 candy dots to the model representing 3 GPS sites. We can use the displacements or velocities of 3 GPS sites to compute the mean crustal strain in the triangle between these sites. We can do this even though there might be discontinuities between the sites. The initial circle evolves into an ellipse because the discontinuities are small relative to the distance between the GPS sites. Finally, we can start with the powdered layer on the stretched fabric and see what happens when we shorten the layer by relaxing the fabric. Thrust faults develop in the layer and the circle becomes an ellipse whose long axis is perpendicular to the direction of shortening. And of course, we can invert the deformation by stretching the layer we just shortened. There are many other explorations that can be done with a simple and inexpensive physical model of one-dimensional stretching and shortening.